provide you like different, because it's hard to pack everything in a few minutes. I'm trying to just walk you through it. The breeding aspect of the research, some of the genetic work is needed for this type of research, and eventually what the genomics are. And I'm going to start with the past, and then going back to the future, current research, and then future, and some of the findings that we have. Now, why is it so important? We have, in 2002, it was a big problem in California. One of the extension people, patent extension people, was told that we start seeing this type of problem in California. This is a cotton peanut field planted right around April 15 or something. 2 weeks later, 3 weeks later, there were this many plants all there. So you end up having from 5 to 10% survival. So imagine the impact of cotton and the effect of the producers in California. So it was a big deal. At that time, we didn't know what it was. We thought it was fusarium. So the people in California started looking at symptoms, and like I said, it kind of resembled fusarium wilt. Basically, the wilting of the leaves, necrosis, dark brown silent problems. So that's the stuff that the symptoms that we used to see. Again, UC Davis, scientists from UC Davis, pathologist Mike Davis, was able to run some tests and identify that the new race, new for California, not for the entire world, was a race for causing these problems. In California, it was known since the 1950s that we had race 1 and race 2. But this race was always associated with Rudnan nematode, which is another warm problem of pest that we have. So race 1 was always associated with Rudnan, and also the type of soils was more sandy soil type. That's the kind of soil that you would find in this race. Now, this new race was totally different. It was a clay soil, a little more heavy soil type. So again, we were found out in race 4. So we started working to find ways to evaluate germplasm, breeding lines. We were eventually able to run greenhouse evaluations, field evaluations. We usually used to do replicated tests, randomized complete flow designs, complete randomized designs for greenhouse. So with that, I think for now, we put in 2011 because in 2012, that's when I found out that I was moving, so a lot of my program was closed down. So some of the data that I have is from 2011, and some of the publications that are just coming along is basically work that was done in California. So we really did an extensive search for sources of resistance. Just to show you some of the green tests, we started using what we call a modified root tip, where we basically have the inoculum levels. You grow the seedlings and the seed in clean soil, and then eventually you dip it in inoculum with race 4 fusarium. The inoculum levels that you use, the conidia, some of you are familiar with fungi, conidia spores, 10 to the 6 to 10 to the 5 conidia spores in the solution, so then drip it, and then you can still start seeing the symptoms of the 4 to 5 weeks. Just to show you also the way the scores that we used to use in these evaluations, based on, again, score 1 to 5, and those are the symptoms that basically you end up seeing in those projects where we used to evaluate. What we got out of that, like I said, we identified sources of resistance. And the commercial side, when this started, like I said, 99% of all Pima cotton. For some of you not familiar with cotton, it's Pima and upland. Everything that's growing here, is all the way from here to the south to the east coast is upland cotton. Basically, that's what we're growing there. And California, from New Mexico to California, you have a chance also to grow Pima. California is the first producer, the #1 producer of Pima cotton. So it was really, again, a big problem for California. So 99% everything that was growing commercially in California was susceptible to this race. So finding this line was really a big hit for us and for the growers. So kind of saved the industry 3 or 4 years, or even more, before they could come out with something like this. that's one of the things that we will find also in our program, in my program, working with different breeders, we will identify germplasma, breeding lines that have the resistance, so we will release public material. And right now we're in the process, I'm in the process of writing a new release with better lines compared to yields, like I said, really competitive in terms of fiber quality and cotton. Before you release anything in California, you need to make sure the fiber quality is number one. Also, you have to have the length, the strength, and the fineness. Otherwise, you're definitely not going to have any success. So, seed or releasing any cotton in California. Just to give you an idea, this is the way, like I said, when you have an infested field, this is the way it looks like. This is the line that 70% or 80% of the land in California used to be planted with this line. So this is one of the nurseries that we have. Like I said, the advance that we did in terms of finding resources and genetic material for this was really great. So I think so far for Pima cotton, we make a lot of progress and success. We have a lot of success. I'm just going to touch a little bit about how, especially in race 4, how is transmitted to the progeny. In this case, we have the source that we found was Pima. We crossed Pima cotton versus Apna, which is Pima S6 versus P1. Doing that with an F1, which is a cross of the two. Yeah, really resistant F1. So that gives you an indication that the trait that you're going to try to breed for is going to be a dominant trait. So it's going to be easy to select through the process. So in the several generations, it will be easy to select. Again, you need to select not only for the resistance at this point, but you start looking for better fiber quality and yield at the same time. So again, I think for this trait, for this specific race 4, I think we found good resistance. Now the process that we're going to follow is again develop a large upland germplasm, introducing the resistance from this PS6 line into upland cotton. Just going to touch a little bit about QTO mapping. Some of you are familiar with that. I'm just going to touch a little bit what it's all about. It's basically, again, looking molecular marker data into progeny, fingerprinting, or what we call genotyping. At the same time, the infection rates that we use, those values, try to associate with a specific progeny. So, well, that's what we call genetic and QTO mapping. And again, when you create that, we're basically able to find or identify those genes in actual chromosomes. Like Trish said, I've been involved in multiple projects. One of the other projects that I've been involved in cotton is trying to come up with molecular markers, try to develop molecular markers to be used for breeding in cotton. So in my lab also, at that time, like I said, we have extensive collection of markers, so we were able to genotype and fingerprint progeny, and then develop populations, like the one that I showed you, across 2 different parents susceptible to resistant, to be able to genotype and associate where the resistant genes or the chromosomal regions that carry or house these genes. One of the things that we did the first time was working with the group in UC Riverside, tried to find, for race 1, we were able to identify using different crossing combinations. This is cotton plants against cotton entries. We were able to identify a QTL chromosome region in the marker associated with a race 1 resistant. And the resistance for this specific chromosome region in some of these markers end up being from 20 to 31%. The other thing that we did also looking at race 4, which again is the most important one, try to locate where in the chromosomes or in the cotton genome this gene, the major gene resistant for PS6 was housed. And I think we believe we found it. It was, at this point, we believe it's a chromosome 14 and 20 markers between P and one of the SSR, 2 SSR race 2. Again, the variation of these QTL ran from 20% to all the way 70%. Again, we're still using in cotton the old technology. This is We're still using SSR. We're still lacking what we call SNPs, more high throughput system. And looking into some of these molecular markers and SSR that we identified, again, this is related to what I showed you, the graph and some of those QTLs or markers associated with REST4. And just to give you an idea of what we're trying to do is if you're able to have a choice to select 100, to put 100 plants in the field, and then you're able to go and use any of these markers as it trace the genes that are responsible for it, with 70% of chances of getting it. You only need to select about 25 instead of 100. So it's a lot of cost effective in terms of the breeding process, reducing the amount of progeny and material to look at it. So just again, just to show you the differences in the cross between the resistant and susceptible. And like we said, most of the susceptible carry a specific allele. Most of the resistant carry a specific allele for each of these lines represent a plant that was isolated, DNA isolation for each plant. So again, because it's not 100% association, you find out that not all the plants will carry it. Sometimes you can, it's up 60 to 70% association. Again, in summary, we have, again, map starting with this one. We believe that we have about 24 SSR markers, and these 24 are distributed around 9 chromosomes. And same thing from REST4, we believe there's about 12 chromosomes involved with minor effects of genes. And the major QTLs that we believe for REST1 and REST4 is probably in chromosome 16, and then for REST4 is probably chromosome 14. Now, like I said, that was some of the work that was already done when I was in California. Now, what are we going to continue doing and try to follow up with the research? Now, we know, like I said, in our group, we know, like right now, like I said, we have access to around 10 major SSRs that we know that will be really efficient in breeding for concerning REST1 and REST4, and a total of about 55 minor genes or markers associated with it. And in our work, also, one thing that I'm also working is with a group, international group from Uzbekistan. We're working with REST3. We think we already have chromosome. I don't want to put it there because I don't want to they say, well, what's the different one? But we believe that there's a lot of common alleles for chromosome 16 for REST3. So we believe we already, again, also identify specific alleles and markers for chromosome 3. Currently, like I said, working with other groups in our lab, we have access to more than 2,500 map loci. So this is the map, again, if you noticed previously, I showed you a lot of gaps in between. Now we have a chance to find maps some of these ones. So we actually can find specific regions, and not only, like I said, pinpoint possible marker or the gene that was more associated, almost 100% with the resistant. And also, again, we have a set of marker genes that not only involved for Sarin, but also involved, I've been working also with the Bruna nematode. The other thing that we're doing, based in previous research, also concentrated in 2 chromosomes, chromosome 11 and 21, which basic everything has been published. We find out that these 2 chromosomes are homologs, what we call in terms of cotton. We find out that many of the small genes are also housed in these chromosomes. We have about 100 back. Some of you are familiar with backs, bacterial artificial chromosome. The fragments that you're able to form in sequence in these back clones, there's about 100 kbs, 100,000. And we have 100 of those from every single region that we know that there's a specific marker that is associated with the back that we have about 100 kbs. So we have over 100 in all these 2 chromosomes that we're looking at. That's pretty much what we're going to, again, the data is already there, just have enough time to analyze everything and publish. The other thing that we're doing in the future, since I moved also to level. I was able to start talking to people in my unit and also with Texas Tech. And I think we were able to establish already an agreement with Texas Tech, and we're going to start looking to establish or to start projects and using the new generation sequencing. And again, the idea is to come out with better markers or biomarkers to identify associated for breeding. But at the same time, look at some of those genes that have different expression. And I'm going to start explaining to you. I'm just going to show you the people involved in the projects. Like I said, we're going to be looking not only to Fusarium, but also to stress, the gene expressed on the different conditions, trying to extract all the RNAs from those roots and leaves. They're showing that kind of stress, and got a transcriptome or database where all these genes are expressed in these different tissues. That will give us a mass database to look at it, so all these markers, everything that we're going to be able to blast and find similar genes in these data sets. At the same time, in those data sets, trying to develop new markers with better precision and expression at the same time, and go back to the progenitors and do the same, what I call genetic QTO mapping. So the type of map that you see with humans, I hope, in the future. You see a lot of things, a lot of markers around each chromosome for copy. Again, that's just to show you that we have an agreement with Texas Tech. We're going to be using the Illumina MySeq and the bioinformatics capabilities that Texas Tech has. At the same time, I think we're also preparing ourselves in our labs and our team to be able to have the necessary resources to analyze all this data, because you're talking about billions and millions of reads and sequences. So I think, like I said, there are 3 phases in this new generation sequence data that I think we covered so far. So we have all the expertise also. We start getting together. Myself, I'm retraining, learning new techniques, new protocols. So we're going to be able to have, like I said, we do have the second level. We have computers and our lab also programs, software programs that are able to take thousands, millions of reads at the same time and do all the analysis to create these mass data sets and look at it. And then just to give you an idea how we're going to start looking into it, if we have susceptible and resistant plants, we're going to start looking at races, race 1 and race 4. Because I already know, again, the response, the genes, of these genotypes, like I said, we have PS6, we have PS79, so we already know the background of these plants. They are resistant or susceptible for one race or another. We're going to try to, again, induce the expression of those genes, remove the RNAs from those, and be able to collect data. Again, just to show you, one of the things also that is going on that from this new funding that I have was I was able to hire a new postdoc. And right now, she's the one, like I said, doing all the work in terms of DNA isolation, RNA, and then getting the libraries ready for the MySeq and everything. And like I said, we have in our lab also the computer and the software to analyze the data. A previews that, like I said, this is not related to the Fusarium, but it's pretty much the same approach. And what we did here was just growing 20 growing plants, about different roots, collecting tissue, 15 days old leaves and roots harvested, and be able to collect more than 4.6 gigabytes of reads. And these reads is about 150 base pair clone. When you start looking at the difference in configs or genes expressed that we're able to capture in roots and leaves, it's about 44,000. When you ask around, you're pretty much covering about 70 to 80% of the whole transcriptome of RNA expressed in those tissues. So I think we're doing pretty well to use the MySeq and to be able to capture most of the genes expressed in these ones. We also start doing some SNP discovery. Like I said, we just start comparing different parents and start looking at how many SNPs different you find in the 2 genotypes or the 2 different parents, 572 installment. We're able to find again with 50% for some coverage to end up having about 6,000 SNPs for configs and leaves and about 4,000 in roots. And then just to give you a figure of the way they also are expressed, when you start looking at expression, between the two genotypes, you start seeing again differences between the two tissues and between the two genotypes. So the two different genotypes. To finalize, just want to tell you what we know until at this point. Like I said, all these different papers that we published in different races that we know about it. We know about race 1, which is again in 4, which is California. We know about race 3, which is in Pakistan. We know about the race 7, which is in China. And also Australia has a really, really bad race, bad action. So we also know that some of that is also a lot of these things also generate data, frequencies, and data that we will use to, again, compare to our data sets and everything that we will develop in the future. Finally, as a summary for the whole talk, I think what we're planning to do, like I said, and improve during the next 3 or 4 or 5 years is working in all these different areas. I think we need to make sure that we also understand not only with race 4, but the same thing we understand in race 1, because each race has a specific gene or major gene that interact with the plant and provide a system interaction. So we need to make sure the whole plant system is covered for all the races. We need to make sure that, again, the SNP system, validate the